Hi, my name's Bruce, and this is a video about giving an old lathe chuck some tender loving care. This is a 4-jaw chuck from a hard-hinge lathe that's about 50 years old. It looks pretty like it's had a hard life. I can see lots of bruises here. I just gave it a quick stone to see what was there, and you can see all these bright spots where the bruises are and so on. And a couple of the jaws were quite stiff, coming apart, so I went to investigate that and found something interesting. Also learning about how chucks are built. So the drive screws, I don't know what they're called, that clamp that drive the jaws, they're kind of trapped in there, and the question is how. If you look on the back, you can see these 4 pins, and they look like this. So it's just a pin with a fork on the end, and then the drive screw just fits in a recess, in a drilled recess. It's not machined, it's not a close fit, it's just a drilled hole. And then that fork engages the drive screw and stops it from thrusting, so it cannot now move back and forth, and therefore when you turn it, it drives the jaw and thrusts against this fork. I thought, wow, maybe these are going to be really tight in, but they were not. They were just a very light press fit, so I just tapped them out with a thin punch, just a pretty thin punch just to get down in there, and tap them out, and they came out okay. The jaws of the chuck are quite beautiful. They feel silky, and obviously they're hardened. I don't even need to put a file on them to tell that they're hardened. They're just beautiful, beautiful fine finish, and they just feel silky. Really nice. And they're each stamped with a serial number, and the numbers match, so I'm not sure if that means it's a set for this chuck, or whether that's just a part number. Well, in fact, I guess I can answer that, because right here it says serial 45885. Beautiful. And there's the hard-hinge. No, that's the model, sorry, that's model, can't read it, model 36HC. And there's the hard-hinge name. And by the way, look at this. Look what I found. Made in England. This little guy is a tourist. I'm in North America. So he's crossed the pond and now lives in North America. So now, taking the number 1 jaw to go in the number 1 slot, with an outside hold, the jaw fits pretty nicely. A little bit of a grab in the middle there somewhere, and there's just a little bit of play sideways, but nothing vertically. But look at this, you turn it around to the inside with the OD clamping, and it won't go in. What the heck? The jaws run on these 2, I don't know what, ribs in the chuck. So the dimension of the slot in the jaw is very closely toleranced, and that prevents any movement up and down, and therefore holds the load on the jaw is going to try and tip the jaw down, and these kind of rails or ribs prevent it from doing that. They hold it straight. So basically the load from clamping the work is transferred into these ribs. The forces from clamping the work, if my finger is the work, the jaw is going to clamp onto my finger, but my finger is going to push back on the jaw with the force from the clamping, and that's going to make the jaw want to do that. And those ribs in the chuck are what prevent the jaw from rotating like that. So there's quite a lot of force. The clamping forces get transmitted through those ribs in the chuck. So when the jaw's in the chuck, load acts here or here, wherever you've got it, and tries to push the jaw down at the outer side, and that loads up onto those ribs, and those ribs prevent it from doing so, from rotating. So a lot of load on those ribs. So here's what's going on. I've got the dial test indicator sitting on one of those ribs, and it's zeroed, and now I'm just going to slide along the rib, and it's half a thou low there, 1 thou, oh boy, and by the end it's 8 thou low. Coming back the other way on this side, back to 0 at the ID, beginning to drop, not great, it's only a thou there, that's 3/4 of the way out. And then whoa, whoa, falling right off. In fact, the dial test indicator is only barely in range. Here it is zoomed in a little bit more. There's my 0 at the ID of the chuck, and then sliding out towards the OD, it's a thou low there, and then plummeting off the end there, oh, nearly 10 thou by the OD. So what I think's happened is that people have been using this chuck with the jaws really far out, and here again the load from the work is pushing the jaw and trying to bend that downwards, and here it's only half the length of the jaw is on the rib resisting that load, so the rib is bent. It's bent down at the end, distorted down at the end, and so right now this jaw is kind of running uphill a little bit up that bend, and then look, it stops there. So when it comes up to the shape of the rib is like this, so as the jaw moves up the rib, it's going to run into the rib's shaped like this. So when the jaw moves up, it's going to kind of bump into the sort of straight part of the rib, and that's why it's sticking. Here's a diagram of what I'm talking about. So here's the rib that the jaw is supposed to run on, and it's bent, and so when the jaw is right at the OD, that's kind of tilted down like this, and then as the jaw moves towards the ID, it's going to run into the corner, if you will, of the bent rib, and that's why it's binding. This part of the jaw is hitting the bottom side of the rib. And here's a look at the bottom side of the rib. This is the rib here, and right beneath my finger on the bottom face you can see a black mark, and that's kind of a divot where the toe of the jaw has been digging into the bottom side of the rib. So what I'm going to do to free up the jaw is I'm just going to relieve that bottom end of the rib so that the jaw can have a better chance of moving freely on the rib. Now that's obviously increasing the clearance, but the only time that's going to become important, that we've already got the jaw bent, the rib bent down here, so the jaw is all, the damage is done, and unless I can rebuild that material, which I can't, the jaw is always going to, you know, do a little bit of a deflection like that at the near the OD. The only way that this would matter is if you were clamping on the ID of a ring, for example, and then the force on the jaw would be in this direction and it would pull it this away, and then you'd have extra clearance here, and that wouldn't be so good. But if you're on the ID of a ring, the jaw is probably further closer towards the ID, hopefully, so I'm hoping that won't matter. And to try to understand why the jaw goes in and slides in one direction, but when it's reversed it does not go. I'm using this surface here of the jaw on the 123 block as a reference, and then just measuring this surface here, which is the bearing surface of the on the rib, and the result is that it's sloped, but that just means that this surface here is maybe not parallel to that exactly. But the bottom, this side here is 1 thou falling off 1 thou more than the top. So my theory is that there's a little bit of wear on the end here because of that hitting that corner, if you will, of the bent rib, and that allows it to sneak past the bend, if you will, whereas if you go the other way around, there's no wear and it jams on the rib, on the bend in the rib. That's my theory. Once again, a picture is worth 1,000 words. So my theory is that there's a little bit of wear on this corner of the jaw, and that enables it to sneak by this kind of bending situation. But when you turn it around, there's no wear on the other corner, and so it won't go. There's a sharp corner here and it digs in to the bottom of the bent rib. That's my theory. Okay, after some very cautious needle filing of the bottom of the rib at the OD, where it's kind of bent down, now the jaw always went on perfectly this way around, and now this way around, just a little sticky, but it goes. And that's good enough for me. I'm not going to take any more than that. So that worked, and I think my theory is correct. One other thing is, what is the face of the chuck doing? So here the dial is zeroed near the ID, and over here near the ID also 0, over here 0, and over here 0. However, if you run out to the OD, we're minus 2 thou there, minus 1.5 here, minus 1.5, minus 2 and a bit, 2 and a bit, three, 2 3/4. So basically the chuck is sort of domed a little bit. The OD is kind of falling away, which also makes sense because basically the same forces that cause the bending of this rib from the jaws on the chuck itself is trying to bend the chuck like this. the whole body of the chuck. And I guess over the years and over all the forces and the number of times it's been used, it's actually distorted the chuck a little bit by a couple of thou, the body of the chuck. So not the end of the world, but what I might do is put the chuck on the lathe and grind the face so that it's flat and parallel, because sometimes you want to register work against the face or whatever. I think that would be reasonable. Run out on the axial face of the chuck is actually pretty good. Half a thou there, a little over half. Oh no, I think that's just a divot. Yeah, about probably 3/4 there. Less than a half. Not bad. A lot of lumps and bumps. The chuck fits onto the lathe on this taper, and there's a T-shaped slot here, and there is a pin in the back of the chuck there. It's just a screw right through, a dog point screw if you will. It's hardened, and that pin engages in this slot here, and then when you come to the T you rotate the chuck into the slot, and that slot is angled back slightly so it pulls the chuck into the taper. And the only trick here is that you have to decide which direction you're going to be turning in, because if you change direction you basically have to rotate the chuck to the other side, because otherwise it's going to come loose. So just line up the pin with the slot, on it goes, and now it kind of feels like it's on the taper. Now you just lock the spindle and then you just tighten it on and it's done. So then what about the taper? Let's have a look. So here's the taper. It's in two lands and there's a relieved section in the middle, and it's pretty beat up. There's a lot of, you know, little marks and divots where swarf or dirt has been caught in there. I don't like the look of that dark mark there. That looks like a rub or something. There's the pin, and you can see, you know, the general condition is not super good. So what I want to do is knock off the tops of all of the, see, look at that there, right there, there's a piece of debris stuck on the surface. Not great. So I want to clean that up without messing up the taper fit. The condition of the spindle nose seems to be quite good. You can see these lines here which seem to be original. Not sure what they're for, but they look like they're still intact. The finish is, you know, pretty decent. There's a scratch there which looks like where the chuck has turned on and carried some debris with it, but it's only a scratch. So all in all, the spindle looks pretty nice. I believe it's a 4-degree taper. I blued the spindle and tried the fit of the taper, and the result is not very good. You can see lots of spots of blue there associated with, you know, bits of debris that are sort of embedded in the surface of the taper, the bore of the taper. There's very little. Most of the blue is on the top, the first land, and there's very little on the second. I put a heavier inking on the spindle with this result. So again, most of the contact is on the first land, not the one deeper. And there's some, look at the big gap there in the, here, there's nothing here. Some contact here, but nothing there. Very little on the bottom land. It's kind of another gap there where that gouge mark or rub mark was. So it is not looking too flash. I would say that needs to be reground. Of course, bluing only tells you what the fit is between the two parts, in other words, relative to each other. It does not tell you whether each part is round or, you know, whatever the shape it's supposed to be. So in order to check that a little bit, I'm just doing run out on the spindle to see if it's at least round. And that looks pretty good. There's a needle width there, but that makes me think that the spindle nose is pretty, the geometry of the spindle nose is okay. There was a little bit of variation in the run out on the spindle nose, just, you know, very small, but it was kind of a little bit random. So I'm checking the axial run out, and look at this. I'm going to grab the spindle and push and pull it back and forth axially, and there's 5 thou of looseness there, which means that the headstock bearings are worn or wrecked. I mean, it runs fine, but there should be no play there. So looks like I have got a new project.